Hello, everybody, and thanks for making time today and joining us for an analog work group meeting. Today, I'm pleased to introduce Dr. Steve Herbst, who is a recent PhD recipient in electrical engineering from Stanford. And he's going to share the work that he's done on the modeling of AMS type circuits in FPGA, which I think is an important topic. Verification of AMS from a functional perspective is always a large challenge in any design realm, and I think this is a very interesting topic that I hope that all will enjoy. So with that, Steve, why don't I turn it over to you?
Thanks, Rob. Just a second, I'll set this up.
Yep, take your time.
Let's see. Right, is this sharing the right screen, or you're seeing just the slides, or?
The slides look good, yeah.
Okay, cool.
It looks good.
Great. All right, yeah, so as Rob was mentioning, the verification topic is really important for chip design, both for digital design as well as AMS design. And in addition to that, before the chip comes back, we also want to be able to interact with the design to develop software and firmware so that we can reduce the overall development time for the product. So the unfortunate thing is that when we're working with a pre-silicon design, if we want to simulate the whole thing, often that's not really fast enough for the work that we want to do, whether it's software development or running very long tests like booting an operating system or verifying operation over billions or trillions of cycles. So what's often done instead is we take digital parts of the design and map them to an emulation platform, which could be a commercial FPGA board like the one that I've shown here, or it could be a commercial emulation platform like ZeBu from Synopsys or Palladium from Cadence. So that all sounds good, but the reality is that a lot of modern designs have analog blocks in them that don't have a direct mapping to these digital emulation platforms. And in addition to that, we can't exclude them from the emulation because they often have complex interactions with the digital blocks in the design. So this might be something like a calibration algorithm, for example. So the result is we need to figure out a way to include the analog blocks in an emulation. And this means that we need synthesizable models for those blocks. So that's really what my research was about during my PhD, was exploring the techniques for modeling analog blocks in an emulation context. And in doing that, I found for some types of designs a bottleneck with the traditional approach to emulation. Came up with a new modeling technique to address that. And then also sort of in parallel with that, I developed an open source framework for emulating analog mixed signal designs on FPGAs, mostly for research purposes, for doing comparisons, for example, between the traditional approaches for emulation and the new methods that I was working on. But I also have, the framework has also been applied to some commercial designs as well. And I'll talk about that a little bit later. So this brings me to the outline for the talk. I'm going to give an overview of the traditional approach for emulating analog blocks. Then I'll talk about the new techniques that I developed during my PhD. Then I'll talk about the open source framework for emulation. And then finally, I'll wrap up with a sort of summary of some applications of this work in academia and industry. So to illustrate how emulation is typically done today for analog blocks, we can start off with just the most basic, sort of the hello world of analog blocks, which is an RC filter. And if we want to include this block in our emulation, then we immediately run into an issue because while we do have lookup tables, flip-flops, and so on an FPGA, what we don't have are user-defined resistors and capacitors, or other analog primitives like that. So we need to come up with some way of modeling the behavior of analog circuits using the stuff that we do have. And the typical approach for doing that is called oversampling, where we take the original circuit, we write down a system of equations that describes the behavior of the circuit, and then crucially, we pick a fixed time step that we're going to use to discretize the behavior of the circuit. And then that ends up resulting in a discrete time equation that models the behavior. So, if we look at how this maps to an FPGA, it's a great fit. If this discrete time equation consists of two multiplications, which can map to DSP slices on an FPGA, an addition, which is also very efficient to implement using LUTs. And sorry, I think there's a little bit of background.
Somebody's got music or noise on or something. Can everyone mute, please? Okay, go ahead. Recording resumed.
Yeah. So I was just saying that there's a good mapping for these this equation to an FPGA, but turns out there's actually kind of an issue with this traditional approach, which has to do with the trade-off between accuracy and throughput. So if we think about in an emulator, typically in an emulator, we're working mainly with digital signals. But if the analog signals we're trying to represent are a lot faster than those digital signals, then we're going to have to take really small time steps in order to capture the behavior of the analog waveforms with enough detail. So that means that we'll have to slow down the emulator a lot to accommodate the analog modeling, which is not a good thing, because still, even though we're trying to model analog blocks, there's probably the bulk of the system is going to be digital. So it means that we'd lose most of the speed up that we were hoping to get from emulation. And sort of the other way that this trade-off can become apparent is when, even for digital events, if we have things like clock jitter that we're trying to model in a high-speed link, in a traditional approach that uses a fixed time step, the resolution of modeling those kind of effects is just equal to the fixed time step that we're taking. So if we want to, say, double the time resolution for modeling jitter, we need to cut the speed of the emulator in half, which is pretty unfortunate, because typically the resolution that's needed to model jitter, say in a high-speed link, is a few orders of magnitude faster than the bit period say of the data being transmitted through this link. So it represents a significant slowdown. So my goal was to kind of come up with some techniques for eliminating the need to take really small time steps to represent analog behaviors in emulation, and instead get back to more of an event-driven style, where if there are changes in digital signals, they are evaluated in the emulator, but we try to represent the behavior of analog signals, even more complex behavior between digital events, without taking additional time steps, or with taking a very small number of time steps. So that brings me to the new techniques that I explored that are in the event-driven emulation space. So I think the first thing to bring up is just what does this look like from an implementation perspective? So conceptually, for the traditional oversampling approach, we have an emulator clock that's running in the background, and this is, say, driving the model of an RC filter that we have, and either implicitly or explicitly, each tick of this emulator clock corresponds to a time step of exactly the same size. So in practice, actually, we don't usually even represent the signal in the emulator because it's just a known fixed value. Perhaps we would count up a total number of emulation cycles, but the actual time is then just some scale factor of that number of cycles. But this looks really different if we want to try to do something that's more event-driven, like what I was talking about, because it means that each cycle of the emulator corresponds to a time step of a different size, and potentially a very different size, because if you imagine, let's say, two digital waveforms that are have a slight phase offset, then they're going to be handled in separate emulation cycles. But it might be that the first time step between, say, the rising edges of those signals is a picosecond, and then maybe you have to wait for most of a period to see the next event after that. So this means that we now have an emulator signal corresponding to the time step, and that is going to need to be fed into the synthesizable models for analog blocks that we're working with. So the other change is, sorry, was there a question? Or? Oh, no, I think
I think you're okay.
Okay. So in the other issue is that if we're taking these large time steps, we need to be able to represent the shape of analog waveforms over longer periods of time than what we would typically have for an oversampled system. And I explored a couple of approaches for this, but what I found worked well is to use a list of spline points for representing a shape of a waveform out to some maximum time step. So, for example, at the start of a time step, we project out the waveform using a couple of spline points to a maximum time, and then the only requirement is that the actual time step that's taken by the emulator is something that's less than that maximum time. We then discard the points that come after that. So even though we're passing around just a couple of spline points, the idea is that they're implicitly connected by an interpolation method, which is used for resolving things like how the models with analog dynamics respond to this analog stimulus. So what I showed through my research was that we can use this concept of spline points as a kind of common language for having emulation models talk to each other, even if they're modeling different kinds of things. So, for example, we can model a static nonlinearity as a mapping from a set of input spline points to output spline points, but we can also use the spline points approach to represent systems that have dynamics, like a lossy channel or a system that's described by state space equations. So, as I was working on this sort of study of different emulation techniques, one thing that I found is that whether I was working on the new techniques or trying to build up comparison models using oversampling methods, that it's not that easy to create an emulator for an AMS system in the first place. And there's a lot of hurdles that you have to go through in order to get one up and running. And that often means that that people just don't really pursue that as a way of speeding up their simulations, because it's not worth it if you have to invest so much time in order to get started. So that really motivated me to develop some tools to make that process simpler and faster. So what I ended up creating was a framework that consists of three tools. They're all open source. They're all available on GitHub and as Python packages. And the basic flow is that you take a system that has a mixture of analog blocks and digital blocks. For the analog blocks, you create synthesizable models for them using a tool called MSDSL, and that produces Verilog that uses a library called svreal for implementing synthesizable real number operations. So at that point, because the digital block's already synthesizable, we have a synthesizable view of the entire chip design, which we can then wrap emulator control infrastructure around and implement on an FPGA using the anasymod tool. And this tool was actually a collaboration with Infineon, and they've gone on to apply the framework to a number of designs on their own within the company. So I'll just, there's not time to go through all of the different use cases for the framework, but I thought I'd just give a flavor for it. So the MSDSL, as I mentioned, is a tool for generating synthesizable models. And it has a number of input modes, but you can use it in its simplest fashion just as a way of writing down discrete time equations. So there's some operator overloading that makes it pretty straightforward to write down expressions in a readable fashion and then generate synthesizable RTL from these expressions. And that's leveraging the library svreal that I mentioned, which is a macro library that provides both a fixed point and floating point implementation of real numbers in Verilog. So I don't really have don't want to go too far into the details on this on svreal, but I just wanted to highlight that if we look at this code sample, which is generated from MSDSL, that there's actually no reference to fixed point formatting information anywhere in these macros. That's all abstracted from the user, so that it makes it easy, for example, to switch between using a floating point representation or a fixed point representation. And this is basically done by, at least for the fixed point side, by keeping track of signal ranges at compile time, and then using that to determine the formats for fixed point signals. With the trick being that this had to be done in a way that was implemented in System Verilog, so it was easy to integrate into existing RTL. And System Verilog, I definitely found a number of pitfalls and supported features, especially relating to real numbers and doing this. So it was an interesting exploration of synthesis support for real numbers. So in addition to supporting these basic arithmetic operations, MSDSL also provides some abstractions for higher level operations. So there's a tool for converting regular Python functions into a synthesizable format. And there's also a tool for generating pseudo-random noise, particularly Gaussian noise, although it's also possible to implement arbitrary noise if you basically provide the statistics of that noise to MSDSL. And there's also a couple of different ways of describing the behavior of circuits as well, that they can be written down as a transfer function. There's also a symbolic differential equation engine that will allow you to describe systems as kind of linear, switched linear systems, where you can have a differential equation system that also includes some conditional expressions. So it's a slight extension of the basic linear dynamical system. And then finally, there's also a kind of netlist-like mode for MSDSL, where it will take a set of analog primitives like resistors, switches, capacitors, and solve the system at compile time to sort of using KVL and KCL. It will generate a system of differential equations, solve it at compile time, and then have an efficient sort of FIR, IIR implementation of those behaviors on the FPGA, rather than say, it's not trying to build a transient spice solver on the FPGA. It's more trying to create a behavioral model using a compile time solve of a switched linear system. So up to this point, I've been just describing how we can generate synthesizable models for analog blocks. But I did also want to talk a little bit about the other piece of this, which is what happens after we have a synthesizable view of the whole chip. So the first part is that we need to wrap some control infrastructure around the DUT that we're trying to test out. And you might wonder, okay, what kind of infrastructure am I talking about? Well, there's some of the infrastructure ends up being a little bit unique for the analog modeling case, because if we're building a event-driven emulator, then it's the case that analog models are able to generate their own events that have to be scheduled so that they appear in the right order. So in this example here, I'm showing a case where we have two different oscillators models that are operating at different frequencies. So as you'd expect, perhaps sometimes the edges of these oscillators coincide, and sometimes they occur at different times. But both of them are going to be making event requests in the form of a time step request that is gathered up by the time step management infrastructure of the emulator. We take the minimum of those requests and then feed it back to all of the analog models. So in other words, perhaps for oscillator 0, it wants to take a time step of 1 nanosecond until its next edge is scheduled to occur. And maybe for oscillator 1, it wants to take a time step of 2 nanoseconds until its next clock edge is going to occur. So the emulation infrastructure will take the minimum of those two requests, 1 nanosecond, feed it back to the oscillator models, and oscillator 0 will see that its request was granted and fire a clock edge, whereas oscillator 1 will see that its request was not granted and will decrement its time step request and try again. So the other piece of this is that when we're working with things like, say, an oscillator where it's generating clock signals, we need to be careful about the way that that's done, because it's generally not a good idea to drive clock signals directly through combination logic on an FPGA, particularly considering that we've got a large digital block that has probably multiple clock inputs to it that we don't want to modify for emulation. So we want to just be able to create a true clock signal that we can plug into digital parts of the design without any modification. So there's some additional infrastructure that's generated for that, primarily with the aim of avoiding timing problems like hold time violation, although also with the goal of making good use of the emulator clocking resources, like the global clock buffers that I've shown here. So that's sort of some of the infrastructure that's needed for AMS models. But I also found it useful to add some features that are more generic for just getting data into and out of the emulator. And the approach that I settled on there was a kind of firmware in the middle approach, where we have a host computer that's orchestrating the emulator at a high level, and it's sending commands over USB to an ARM core, which is on the FPGA. And then the ARM core itself is running firmware that interacts with the programmable logic on the FPGA. So this sort of provides a hierarchy of trade-offs of flexibility versus performance, where we can make changes and see them immediately on the host computer, whereas we can modify the firmware that's in the middle and see maybe the compile time takes is a few minutes to both compile it and load it onto the FPGA. But that's a lot better still than the potentially hours or maybe even a day to build the bit stream for the programmable logic on the FPGA. So it's, I guess, kind of one of the strategies that I've found as well is that I could start off by prototyping features in Python on the host computer, and then depending on whether those features were becoming a bottleneck or not, I could start to push them further into perhaps into firmware on the FPGA, or maybe even into programmable logic. So the emulator infrastructure that's generated by anasymod makes it pretty easy to do this by auto-generating a lot of the firmware that is used to interface between the host computer and programmable logic. And it also kind of wires up the programmable logic to the ARM core in an automated fashion. So to wrap up, I wanted to talk about a couple of applications of this framework. So it's been applied to 6 commercial designs at Infineon, and also 1 academic design within Stanford, which was a high-speed link. One other thing I would add is I actually just recently wrapped up with a project with Xilinx to apply this to one of their high-speed link designs as well. So I'll just show an overview of 3 of these that cover a variety of different types of analog use cases. So the first one was a firmware-controlled flyback from Infineon, where in this case they wanted to develop they wanted sort of a platform that would make it easier to develop firmware that runs on a digital controller that interacts with a flyback converter. And at the time that I started on this project, they had an existing setup where they were simulating the flyback converter at SPICE level, and then had a SPICE plugin that was running C code to model the behavior of the firmware that was controlling the flyback. But this wasn't very fast, so it wasn't necessarily a effective tool for doing firmware development. And they asked me to look at whether emulation could be used to speed up the simulations and make it easier to do firmware development. So in this case, the answer was that you could get a speed up of about 3000x using MSDSL to generate a model for the flyback converter using a SPICE-like netlist that's solved at compile time. So I guess the data point for this ended up being it's on the about 3 orders of magnitude speed up for modeling this type of system. I also looked at an NFC-powered chip from Infineon, where in this case it was a little bit different. They had a hardware in the loop emulator that included physical coils and rectifier circuitry, load modulation, but they wanted to explore whether it was possible to fully virtualize this emulator so that it would be easier to distribute to developers or potential customers, and also easier to change analog behaviors without PCB modifications. So they had they were already doing real number modeling in Verilog for simulation purposes for this. And what I found was in this case, we could get a speed up of about, say, 500x between 2 and 3 orders of magnitude by building synthesizable models with MSDSL. And the last application that I wanted to talk about is Dragonfly, which is an open source high-speed link receiver that was developed at Stanford. So in this case, the key behaviors that had to be modeled were a lossy channel, which ideally we would be able to describe according to S parameters that were measured in the lab. And we also needed to model the sort of non-idealities, both in terms of the noise of the ADCs that are used in the high-speed link, as well as timing jitter and when ADC samples are taken. So this is really where the event-driven emulation that I was talking about earlier, I think shows its best performance, because we're able to completely eliminate the trade-off between timing resolution for modeling jitter and the throughput of the emulator. So this achieved the best speed up of the 3 use cases of about 5,000x compared to our already optimized real number models that we were using. I should also mention that just recently, as in about a week ago or so, I finished a project with Xilinx to apply this to one of their high-speed link designs, and found a similar speed up, actually a little bit better than this, for working with a larger commercial high-speed link design. So it seems like, at least with those 2 data points, that the event-driven emulation approach can has a path to scaling for larger designs. So to summarize, I showed over a couple of applications that AMS emulation can provide a speed up of a few orders of magnitude. But in order to achieve that speed up, we need to use the right modeling techniques. And in some cases, that means using the new event-driven emulation approach that I talked about earlier. And the other piece of this is just that building synthesizable AMS models is not always easy. So that had motivated me to create an open source framework for AMS emulation, so that it's easier for people to achieve these kind of speed ups in the first place. So kind of looking forward, this is, I wanted to leave some time so that we could discuss sort of what might be some good next directions for this project, because as Rob mentioned, I've graduated at this point, so I'm not actively working on the open source tools at the moment. But at the same time, it's a pretty complete set of tools that has been applied and is still being used at Infineon. So I'm sort of curious to have to hear some thoughts on sort of what I should do with these open source tools going forward, particularly both from the user side. If there are any folks that are interested in trying out these tools, kind of think about how that might work. Like maybe I can connect them to some students who are currently at Stanford who might be able to provide continuing support for that. But also on the developer side, just thinking about how to integrate these tools with some of the new open source chip design tools that have come out in the last couple of years, and also just in terms of making it easier to create models. Just trying to continue to raise the level of abstraction for model generation so that it's easy for someone who has background just in Verilog level simulation modeling to approach. So with that, I'll end the talk and would be happy to take any questions.
Steve, thank you for an excellent and very informative talk. I think it's great work that you have accomplished as part of your studies and are sharing with the community. It certainly is a difficult and challenging area. So I'd like to open it up to questions from the audience folks might have.
I have two questions. One is how much development effort is required? Like, for example, how many engineers? What is the turnaround time? This is number one. And the other question is that is there any limitation on the size of a circuit you can emulate? The two questions, yeah.
Yeah, those are both great questions. So on the first one, I have a recent data point. So as I mentioned, I just recently wrapped up a project with Xilinx to apply this to one of their designs. So in that case, the answer was, it took me 250 hours to model their commercial design. So it's about, if I was working full-time on it, would be about maybe a month and a half. A little bit longer than would be ideal, I think. But when I looked at the time that I spent on that, actually a large portion of the time was on preparing digital aspects of the design. This is also a common thread that I found as well for the academic design and for the designs I worked on at Infineon. So that's sort of just in general highlighted to me the fact that it'd be great, even just from a digital emulation perspective, if we had some open source tools that just made it really easy to get a digital emulation running. We can kind of separate out almost these problems of at a basic level, get a digital emulation running. And then in addition to that, we should have tools that can generate synthesizable analog models so that they can feed in upstream of that digital emulation process. So yeah, I think that definitely seems to be an area where there's still a lot of work that could be done on the tooling side to just make it easier to handle multiple clocks in a design without having to really go in depth and learn the clock tree as an outside user. And there's also a lot of just syntax discrepancies between FPGA synthesis tools and ASIC synthesis tools that take a long time to smooth out. So I think that was the first question about how long does it take. The other question about the size of the chips, I think there is definitely a limitation when using FPGA boards that the largest FPGAs have perhaps a 1 million or a small, maybe a few million lookup tables on them, which is not enough to emulate very large chip designs. It's enough for small commercial designs. So I think another future direction would be looking at using these synthesizable models in a commercial emulator context where those systems have the capacity to emulate a full chip design.
You're recommending, say, Palladium and the like?
Yeah, I think that would be interesting to look at. Yeah.
Thank you. Yeah.
There's a trade-off there, though, that I should mention is that in general, there's about a 10x performance reduction to go from a custom FPGA setup to a commercial emulator.
Other questions?
Oh yeah, just out of curiosity, yeah, how much utilization did you have for this design on the ZC706?
Let's see.
For the mixed signal part in particular, yeah.
See, I think I probably have something in here about that. I don't remember where exactly, but it's. I think I saw something about that.
Oh.
Okay. Yeah. Yeah. So looks like, yeah, I guess there were actually a couple of different versions of the emulator that I built. I guess the highest performance one is this middle one, the high level fixed point design. So in that case, the DSP was maxed out. That was a design choice where basically I was tuning the parallelization of, or adjusting the parallelization of the analog models to max out the DSP resources so that I could get as much parallelization as possible, given the FPGA's DSP. But in terms of the LUT resource utilization, it was about a little bit less than half. And I think there's actually kind of an interesting trade-off there as well, because what I found in some of my work on commercial applications is that the digital parts of the design, in other words, stuff that we're not changing, that we're just trying to pull into the emulator, mostly consumes LUTs. So if the analog models can kind of stay out of the way of that, that's good, because it improves the chances of being able to fit the design onto the FPGA. So it is kind of a nice feature that, if the analog models mostly consume DSP blocks and the digital parts of the design mostly consume LUTs, they're at least not fighting for the same resource.
And out of curiosity, for this one, did you have to massage your model a bit to make the fixed point model fit in the DSP resources? Was that challenging?
Yeah, I did have to. I think I went through a couple of cycles on that. I mean, it's not very difficult to estimate the resource utilization, but it's also not automated. So it's like I would have to make a guess of like, okay, I think this is going to use about this many DSP slices, and then maybe iterate on that a little bit once.
I see. I think.
Other questions? So Steve, thanks for the presentation, and also if you can make the slides available to me, I will work on getting this posted for folks to look at, as well as the video. You asked a question about possible next steps, and relative to the framework that you've created and the modeling as well. There's definitely interest from the CHIPS Alliance side in your work. We are actually starting up a work group on FPGAs. We've been working on trying to get some different company members participant in that, which will focus on, in particular, open source tooling to address some of the concerns that you correctly highlighted here. So I think, if that's something that's of interest to you, we would be, very welcoming to have, your participation in that group, and to help us move that forward. So I would be very happy to introduce you to the right folks that we have on board to try to help get this going.
Sure. Yeah, that would be great. Thanks.
So no, thank you. And also I will look at your charts. I'm kind of curious about the time step work that you did. My background more is in static timing analysis, and then originally gate level, then into transistor. So it looks very similar types of modeling approaches that were used for, or considerations, I should say, there's a better way to put it, for handling that as well.
Yeah, it's an interest. I think it's definitely an interesting area, because it's a little bit counterintuitive. I think that when you're looking at direct logic analyzer traces from an FPGA, that the emulator clock is always running at a fixed frequency, but it's representing something which has no connection to that frequency. So another, the traditional emulators run at either a fraction of real time or some multiple of real time, whereas in this case there's a separation between the physical time that this is being taken by the clock on the FPGA versus the thing that it's modeling, which took it took some time to sort of wrap my head around that and build some debugging tools to better understand what's happening. So.
Although I appreciate the innovative thinking there on that specific point, because it, certainly I don't think that's been considered in the past. So I do appreciate that. This is maybe a dumb question, but would you look at any other different interpolation methods possibly for the waveforms, or just kind of stuck with what you suggested? Yeah,
I looked at a couple of different methods for that. So I guess there's both. There's kind of the general question about just how do you represent analog waveforms in a way that is richer than a piecewise constant waveform.
Right.
Overshot here, but then there's also the, so for that, I looked at using both polynomial coefficients, so kind of projecting out just from time 0 versus using spline points. In this particular case, I found that the spline points ended up lending themselves to a simpler implementation because they, for example, if you think about modeling a nonlinearity with spline points, you can just apply the nonlinearity to each one of the spline points, whereas with polynomial coefficients, it's a much more complex transformation that ends up also, it turns out, consuming more hardware resources. But in terms of the interpolation, that's actually a really possibly application dependent even question, because if I only tell you that there are certain points that appear on a waveform, any method of connecting the dots is still consistent with that. So it's almost like there's some natural shape of analog waveforms that's kind of described by the interpolation method. And it could be that, the approach that I used was just using piecewise polynomial interpolation without any assumption about what the underlying waveforms look like. But you could also imagine a case where if you know that there's a certain class of waveforms that you're trying to represent, that given a couple of points on those waveforms, that you could reconstruct the shape even more accurately than without knowledge of the shape of the waveform.
No, that makes sense. I was asking my question in part because I know, some years back when, in my role at Sun and Oracle, we had built our own cell characterization application. And, one of the studies was looking at different interpolation methods to improve the accuracy of the model representation of the underlying circuit. So that I appreciate the commentary on this. So are there any other questions today for Steve?
That was great work.
Oh, thank you.
Yes, very interesting ideas. Yeah.
No, I truly enjoyed the presentation, Steve. Thank you so much for bringing it to us. It was
Thanks for
great work
inviting me.
that you did.
Yes.
Thanks.
Thank you, Steve.
So with that, we'll wrap up today's meeting. Look to see a meeting in 2 weeks again from today. Mohammed Qasim's going to be coming in and helping me run this. So I appreciate that. And I'll look to get out an agenda for that meeting. So if there aren't any other questions, I want to thank everyone for their time today. And Steve, again, for an excellent presentation.
Thank you.
Take
All
care,
right,
Steve.
Bye.
Thanks for
Bye-bye.
having me.
Thank you, everybody.
Bye.